I'm sorry for the wind. Hey, welcome to Math Life Balance and to the series K-Theory Wonderland. Today I want to tell more about the magic of group completion, which we have already seen in one of the previous videos. Watch it if you haven't seen. And as always, please don't worry if you don't understand the math I'm telling, and don't blame yourself. It's totally fine, but if you want to learn more, you can look in the video description and find extra references there. Let's see. So, as you remember, group completion was a magic spell, which was taking a monoid and making it into a group. We saw two examples of it. So the main example was that if you take natural numbers, then group completion makes integers out of natural numbers. And a more complicated and abstract example was that if you take the space of projective modules over a ring, then its group completion is the K-theory space. So, as we discussed in that video, group completion is a magic spell of formally adding inverse elements. However, there is a natural example in between, that is the space of finite sets. So this is a space whose points are finite sets, and the paths are isomorphisms between those finite sets. It's formed in a similar way like this space, but instead of projective modules, we just take finite sets. And the question that I want to discuss today is, what is the group completion of this space? To answer this question, we will wander away and meet another classical object in mathematics, more precisely in topology. That will be the homotopy groups of spheres. One of the biggest problems in topology has been to understand the chaos given by the homotopy groups of spheres. And while there is a lot of progress made in this direction, researchers are still trying to find more patterns among the homotopy groups of spheres. The first step to decrease the chaos of all the homotopy groups of spheres is to consider the stable homotopy groups of spheres. They are defined as follows. So they are given, the ith stable homotopy group of spheres is given by pi n plus I of Sn. That is the classes of maps from the sphere of dimension n plus I to the sphere of dimension n when n is big enough. So for example, the zeroth stable homotopy group will be given by classes of maps from Sn to Sn, and that is just the integers, and those are classified just by the degree. And the first stable homotopy group is Z mod 2, and they are known approximately up to 90th stem. All the stable homotopy groups of spheres can be encoded together as homotopy groups of a certain space, and that space is called the sphere spectrum. So the sphere spectrum is a space that is denoted as a beautiful S, with the property that its homotopy groups are exactly the stable homotopy groups of spheres. And this space plays a very important role in modern homotopy theory, and you will see a glimpse of that in the end of the video. Now let me tell you, what does this have to do with the question asked in the beginning? As you remember, we were wondering in the beginning of the video, what is the group completion of the space of finite sets? And the answer is given by the Barratt-Priddy-Quillen theorem. And I really like the name because of the spelling. Look, there is double A, double T, double D, and double L. Everything is double. So the theorem tells you that if you take the space of finite sets and consider it as a monoid with respect to this joint union of finite sets, and then take its group completion, then what you get is the sphere spectrum. so the space that encodes all the stable homotopy groups of spheres. I find this result very surprising and beautiful because, first of all, it again shows the power of group completion, because we took something as simple as finite sets and got out of it something as chaotic and complicated as stable homotopy groups of spheres. So this is, finite sets are a very simple object, and the stable homotopy groups of spheres encode lots and lots of complications. This theorem is one of my favorite results in mathematics because it relates such fundamental objects as finite sets and homotopy groups of spheres in an unexpected way. We can see a small instance of this isomorphism if we just look at π0, so on connected components. On one hand, we have π0 of the group completion of finite sets, which is the group completion of π0 of finite sets. But this was a space whose points were finite sets and paths were isomorphisms of finite sets. So its set of connected components will be the set of finite sets up to isomorphisms. So this is just they are indexed by natural numbers. And so we get just the group completion of natural numbers, which, as we know, is given by integers. And this is indeed the 0th stable homotopy group of spheres, which is, as promised, π0 of the sphere spectrum. At this point, you might ask, what does this story have to do with K-theory? And the honest answer is that this story is more about the group completion, and K-theory is a result of group completion. But we will see a deeper connection between K-theory and stable homotopy groups of spheres in one of the future videos. Stay tuned! It turns out that on a philosophical level, this theorem opens a new perspective on the connection between homotopy theory and algebra. Because modern research in K-theory and around it relies on the idea of replacing integers with the sphere spectrum. So in retrospect, on replacing natural numbers with finite sets. To get a glimpse of this idea, I invite you to watch together a research talk by Lars Hesselholt, where he talks about this idea. Enjoy!